So in this video, we're going to do Chemistry 1151, sections 8.3 to 8.4. So this section, we're going to be talking about solubility, so everything that could affect the solubility. So solubility is how much solute that you can put in a solvent. Basically, solubility is how well does it dissolve. How much can you fit into that much of your solvent? So for example, how much salt can I fit into water? Like how much salt can I pour into water where it it stays a solution, a homogeneous mixture. It doesn't become heterogeneous. So like if I'm pouring in a bunch of NaCl into a cup of water, we can pour and pour and pour, and at some point we're going to get to the point where the water can't hold the NaCl anymore. And so at some point we go past the solubility and you would have, so if you keep pouring, at some point you would have water and then you would have like NaCl solid kind of at the bottom. And in this water, we would have NaCl ions hanging out up here. We would have these ions just kind of hanging out in our water. Let me remove the H2O from this so that it's a little easier to see what we're doing here. But we would have those ions hanging out, but then you would have this solid at the bottom. We would call this solution, we would name this solution as fully saturated, meaning I can't put any more in there. If I put more in there, it's just going to turn into a solid at the bottom. So a saturated is the maximum number of solute you can put in there. Now you don't have to have the solid at the bottom to have a saturated solution, but the part above that solid would be fully saturated, meaning I can't hold any more. The water cannot hold any more sodium chloride. Unsaturated would be I can keep adding in, so it doesn't hold as much, it doesn't have as much as it could possibly hold. So we can talk about solubility in terms of this rule of like dissolves like. This is a general rule, and it's really more like a spectrum. In real life, it'll be more like a spectrum. You'll see that in 1152. You'll see it's more like a spectrum. So like sometimes something dissolves better, not 100%, but maybe better than other things. But in general, we can say like dissolves like. That means that polar dissolves in polar, and nonpolar dissolves in nonpolar. So like dissolves like means polar, and then let's say polar and like charged stuff in polar solvents, and then nonpolar in nonpolar. So if you are similar to the thing you're trying to dissolve with, you're more likely to dissolve. For example, salt and water dissolve well because water is very polar and has lots of positives and negatives, partial charges, and then the salt actually has lots of positives and negatives too. So this negative, chlorine, would attract the hydrogen, the positive side of water. You can see the little dipole showing you the positive side. Then this sodium is positive, so it would attract the negative side of water. And so they're similar because they have positives and negatives, so they dissolve really well together. Oil doesn't dissolve in water because it doesn't have positives and negatives. It's nonpolar. So oil stuff would dissolve better in oil stuff when water dissolves really well with other charged things or polar things. You can have some molecules that do have oxygen and nitrogen. They can do some hydrogen bonding. So if you can hydrogen bond with water, you're probably going to be more likely to dissolve in water because you're similar, right? So we have a similar language we can talk, which is hydrogen bonding. Usually it's just the small molecules that do this. If you get really, really big, like lots of nonpolar carbons over here, it might not dissolve in water, but if it's small, it can dissolve in water. So if it's a very big chain of C's and H's, probably less likely to dissolve in water. Even if it has an OH on the end or something, if it had a lot of carbons hanging off, it's got big nonpolar region, like all that's nonpolar, it probably would not talk to the water very well. So if it's a small molecule, though, it usually will be okay. If small molecules with O's and N's in them, they're usually able to hydrogen bond. Nonpolar compounds like other nonpolar things. So octane, which is nonpolar, likes carbon tetrachloride because it's nonpolar. They only have London dispersion, so they'll mix together because they understand each other. Like, oh, you only have London dispersion, I also only have London dispersion. And so they can mix together really well. But like octane and water are not going to mix because they're very different. This slide, it seems a little complicated, but we've talked about this before. If you are putting together more stable stuff, then it's going to be exothermic. So if when you're so solvation is the act of dissolving. So when you dissolve something and it releases energy, so if separating the particles doesn't take a lot of energy and the dissolving it releases more energy than the energy you need to separate them, then you get exothermic. So basically this process would be more stable after dissolving. And you don't need to worry about how to tell what that is. Just know that dissolving can be exothermic. Dissolving can also be endothermic. So this would be less stable after dissolving. It takes a lot of energy to get it to dissolve. So maybe like sugar in water, you're thinking about this. To get sugar to really dissolve well in water, it's got to be, you got to heat it up. You got to give it some heat. Versus salt and water doesn't really matter. Sometimes we do have more solubility in warmer conditions, but you can dissolve salt in water. Like the ocean is salty, but also very cold sometimes, right? So it's a little bit different. So don't worry about too much about this. Just know it can be exothermic and can be endothermic. And then there are additional principles. We'll go over this a little bit more in class, but you have on the back of your periodic table, your formula sheet, actually, it's not on your periodic table, it's on the formula sheet. You're going to have a list of ionic compounds that are soluble versus insoluble. Soluble means, so soluble means it does dissolve. And so the state of matter would be aqueous if we're talking about dissolving in water. Insoluble means it does not dissolve. So the state of matter would be solid because it would just be like sand and water, for example. It'd just be like solid hanging out. So we'll go over the actual formula sheet you have in class, but these basically rules. You're gonna have to remember your polyatomic ion names and formulas because it's gonna tell you the name and you gotta be able to recognize when we see that name, what formula does that go with. So I'll say just a little note here. Memorize polyatomic ions. If you don't have them memorized yet, or you maybe have them memorized, but you forgot, go back and look at those again, because we'll definitely look at those more. And then these things you kind of know already. For example, temperature, right? Generally, in solids, solubility increases as temperature increases. And so that means that like you can dissolve more sugar in hot water versus cold water. Like, so you know this. If we're talking about solids, it's usually hot is better. That's not the case for all of them, but it's usually, generally, the case. And then if we have a solid at a high temperature and we cool it down slowly, what we can get is called a supersaturated solution, which is more than you should have. I used to say that my great-grandmother made supersaturated sweet tea. It was so sweet that you couldn't even imagine how she could get that much sugar in there. And so she would heat it up and then she would let it cool really slowly on the stove. And if you mess with her tea or you put it in the fridge too early, she would get mad at you, right? So you would have to, she would be waiting until it was really room temp and then she would cool it further in the refrigerator. And so that slowly cooling it allows it to hold on to more sugar than it normally would. And then with a gas, you know this too, it decreases with increasing temperature. So a cold soda has more CO2 dissolved or bubbly. A warm soda is flat. It's got less carbon dioxide dissolved. It's flat. And you know this, right? If you leave your soda just sitting out, the CO2 will escape. But if your soda is warm, the CO2 is more likely to escape. So we cool it down, we slow those particles down to keep the CO2 trapped in our water so that we have our bubble, our soda is bubbly. And then we also pressurize your soda, right? So we keep it cool, but we also keep it pressure because if we keep it high pressure, we're trapping all the CO2 down in there. If you have low pressure, you open that can, your CO2 is going to escape. And so you're going to have lower solubility. It's going to go flat. I hope that makes sense. You know this stuff already. So don't worry about the Henry's law and stuff like don't worry about that. You understand cold soda, unopened can, more CO2. The longer the can stays open, the warmer it gets, lower CO2 amounts in the soda.